continue chapter 2, which is design principles of dams. So let us see. Okay, so just we will see detail, just brief explanation on concrete dams and embankment dams. So when we say concrete dams, those dams which are constructed mainly from high concrete structures. So high concrete structures would mean RCC. It could be reinforced cement concrete structure and also other related structures. So what are the main forces acting on concrete gravity dams? So these are the main forces which are acting on concrete gravity dam. So the first one is self-weight of the dam, which is dead load. And the second one is water load or water pressure. That includes hydrostatic pressure, uplift pressure, sediment load or silt pressure, and hydrodynamic wave load or wave pressure, wind pressure, seismic load or earthquake force, and ice pressure. So these are the main forces acting on concrete gravity dams. So from these forces, you may have just resisting forces and also driving forces. We will see the detail. Okay, so before we go to the detail, let us see classification of loads. So you have three classifications: primary loads, secondary loads, and exceptional loads. So primary loads are self-weight, water load, and uplift pressure. So these are the primary loads you can find in any dam structure. If you have a reservoir, then you can find whether it is full or just somewhat up to normal pool level or below, you have normal loads. Okay, secondary loads: silt pressure, wave pressure, and wind pressure. So these are secondary loads. You may have or may not have, just site specific. So silt may be accumulated if the river is just suspected or just damaged by erosion, etc., upstream of the reservoir. And wave pressure, similar, and wind pressure. And exceptional loads, this is just extreme, just under extreme damage level. You may have earthquake load, ice pressure. So these are exceptional loads. Okay, so now let us go to the detail. So in accordance with the load classifications, now let us see the formulas. So the first one is primary loads. We have self-weight. So self-weight means just gamma times volume. So we will consider 1 meter length of the concrete dam. Then you have area times length. You have then length will be 1 meter. So just gamma times area. So we will divide the cross section of the dam into regular polygons just for calculation purpose. You may have triangular, rectangular, or trapezoidal cross section. So W1 gamma of concrete times area 1 of the cross section, and W2 gamma of concrete times area 2, W3 gamma of concrete times area 3. So if you have area 4, you will proceed like that. It goes on like that. So where gamma is just the unit weight of concrete. So it may have 23.5 up to 24 kilonewton per meter, depending upon the nature of concrete, whether it is highly reinforced concrete or something like that. Okay, so the gravity dam is mainly subjected to the following main external forces. Let us see. If you have water reservoir, then you have water load. Okay, then self-weight of the dam, which is W, then uplift pressure, then you have wave pressure, wave load, then again you may have sediment or silt pressure, which is just acting to the body of the dam, just in front of the dam as a thrust force. So sometimes wind may act on both directions, either from upstream direction or from downstream direction. So this is wind load. Sometimes you may have earthquake. So if the area is suspected to earthquake action, then you may have earthquake. So this earthquake may be just horizontal or vertical disturbance. So it may create a disturbance on body of water. Okay, so next one is water load or water pressure. So under this, just you have hydrostatic pressure, which is just hydrostatic pressure, which is triangular in distribution, you can see in this one. So hydrostatic pressure, which is half gamma W times Z1 square kilonewton per meter, acting at Z1 over 3, which is 1/3 of this triangular distribution. So this is gamma W times Z1, then this is Z1. So if you multiply area, you will get this value. So the centroid from the base of the dam is 1/3 of Z1. Why we take from the base? Because this hydrostatic pressure will create what? Moment, clockwise moment about the top of the dam, above the base. So just we will calculate moment about this point. We will see later on. So downstream, similarly, it is just acting opposite to hydrostatic pressure in the upstream, which is half times gamma W times Z2 square at Z1 over 3. Okay, so where gamma W is unit weight of water, which is taken as 9.81 kilonewton per meter cube. So you can take. So sometimes the gravity dam may not be just vertical. Sometimes if you have sloping upstream phase, you will have water load PV1 and PV2, which is acting on this sloping phase. So you have PV1, PV2. So you can calculate gamma W times area 1. And PV2, similarly, you can calculate like that. And downstream also, PV prime, you can calculate on this downstream sloping phase, it will act this PV prime. So, but if you have vertical upstream phase, you don't have PV1 and PV2. Only hydrostatic pressure on the upstream side of the dam. Okay, the third one is uplift pressure. So seepage and uplift load may just create what? Clockwise moment, which is driving moment on the structure. So we will see 3 cases. The first one is with drain. If you have drainage gallery, then you will have this distribution of uplift pressure. So at X distance, you may have drainage gallery you may provide. So this drainage gallery is important in reducing uplift pressure, and also after operation, you may use this drainage gallery for inspection purpose. Just you can install tensiometer, piezometer, and temperature instrument, etc. So drainage gallery just has an important big advantage in concrete gravity dam in reducing uplift pressure. But if you don't have the drainage gallery, then the uplift pressure may be full. We will see in the next case. So under this formula, where KD, which is drain coefficient, 0.33, which is according to USPR. So you have 4 areas. So you will calculate U1 gamma W times ZDT times A1. So once you have ZD using this equation, drain depths, you can calculate. So in each formulas, you have uplift pressure. So where Z1 is upstream water depths or head water depths, and Z2 is downstream water depths, okay? Downstream water depths. So this is important. Okay. Case 2 is, which is without drain, just with tailwater. So without drain, if you have just linear distribution of uplift like this. And without tailwater, if you don't have tailwater 0, then it will be triangular like this. 1 area, here 2 areas. So these are just without drain, if you don't have drainage gallery. But sometimes you may have just tension crack. So if you have tension crack, if crack not extending beyond the drain, you will have this uplift pressure distribution diagram. So you will have 5 areas. So the crack length, this one, is not extending the drainage gallery, which is this one, 8 plus 7 meter, which is 15. So sometimes you may provide. Okay, next one is according to US Army Corps of Engineers, uplift pressure distribution with drainage gallery for no cracking, you will have equations. So you will compare drainage gallery height with respect to tailwater. So if Z3 is more than Z2, for example, if drainage gallery height is more than tailwater depth, you will use this equation. Otherwise, if it is less than, you will use this equation. So under this equation, K means drain coefficient, but we will consider drain effectiveness expressed as a decimal. So why we take drain effectiveness? All drainage gallery may not be effective 100%. So we will take drain effectiveness. For example, if a drainage gallery is 60% effective in minimizing uplift pressure, then drain coefficient will be 1 minus drain effectiveness will be 0.4. Then you will substitute in this equation in K value. So this is just the uplift pressure distribution diagram as the previous one. Okay, the second one is USACE uplift pressure distribution with foundation drain near upstream face. Sometimes near to the upstream vertical face, for no cracking, you may have drainage gallery, which is X distance. So just we will check when X is less than 0.05 Z1, if Z3 is more than Z2, which is drainage gallery height, more than tailwater depth, you will use this equation. Otherwise, if it is less than, you will use this. But the first step is you have to check X less than or equal to 0.05 Z1. Otherwise, just you will use the above formulas. Okay, the next one is with cracking. So just the uplift pressure distribution with cracking not extending beyond drain. So this is just as we have seen in the previous uplift pressure distribution. If you have crack links not extending beyond gallery position, you will use this equation. If Z3 is more than, you will use this equation. Otherwise, if Z3 is less than, you will use this equation. So X is drainage gallery position, and L crack is length of crack, and L is the bottom dimension of the dam. So the rest as usual. So if length of crack is zero compression length, which means zero compression length, you have this one. Otherwise, if it is linearly changing, then you will have a change in compression and tension. Okay, the next one is secondary loads. So you have sediment load. So just sediment may be accumulated in front of the dam. So this generates a horizontal thrust or PS. So using this equation, you can calculate 1/2 Ka submerged unit weight times ZS square. So why we take submerged unit weight? The sediment is fully submerged underwater and acting at ZS/3 above the plane. So active sediment pressure is just using this equation, you can calculate because it is in front of the dam, which is actively just pushing the dam structure. So this is the equation 1 minus sin PS over 1 plus sin PS. PS is angle of internal friction of sediment. So where gamma S prime is saturated unit weight minus unit weight of water, where gamma S is sediment saturated unit weight. So PS is angle of internal friction or angle of repose of the sediment. So most of the time, saturated unit weight of sediment may be taken as between 18 up to 20 kilonewton per meter cube. Okay, so hydrodynamic wave load, this is just a wave. So it is generated by wave action against the dam body. So sometimes over water surface, you may have wave that will be generated, and this will just push the dam structure. So this is pressure of the wave, but you have to know wave height, HW. So this HW is dependent upon wind speed and fetch length. So what is fetch length? Fetch length is this one. If this is the dam structure, then the stretch of water up to the last point of the reservoir. Actually, it is average. You will take 3 degree, just draw fetch 9 fetches with 3 degree each. Then average of this, you can have average fetch length. So this is throughout the reservoir area, the reservoir surface area. You simply draw 9 fetches at 3 degree each from this one. So finally, you take average. So we will use average under this formula. So wave height will be calculated first, 0.032 times square root of UF, etc. It goes on this like that. So this is the expression if fetch length is less than 32 kilometer. If it is less than 32 kilometer, you will take this equation. Otherwise, if it is more than 32 kilometer, you will use this equation. So once you have the wave height, then you can calculate wave pressure, which is P wave. P wave is 2 times gamma W HW square, which is acting at 0.375 above still water, which is above this water level. The wave pressure is acting on this dam at this height. So where U is in kilometer per hour and F is in kilometer. Okay, wind load. When the dam is full, wind acts only on the downstream side, thus contribute to stability. So when it is full, wind may act from downstream side. Then it will act as a stability, which is just resisting these forces. So thermal and dam foundation interaction effect. This is the last one, which is unusual load combination, which is secondary loads. Thermal. Sometimes temperature of dam body may be increased. So that's why just pre-cooling and post-cooling procedure is undertaken during construction. So during construction, pre-cooling and post-cooling should be accomplished. So temperature in dam concrete may be increased, and the dam just temperature and dam or foundation interaction effect. On the base contact also similarly maybe just affected foundation shear and also temperature, etc. So this is just free body diagram with upstream vertical phase. If you have upstream vertical phase, you don't have the PV1 and the PV2, just hydrostatic pressure, sediment, uplift, etc. If you have the earthquake, you can add wave pressure, you can add, but no water PV1 and PV2 in upstream side. Okay, free body diagram with upstream sloping phase. This is just a sample. Just we will have illustrative example on this. So this is just how to draw the free body diagram with upstream sloping phase. PV1, PV2, PVS you have. Otherwise, if it is vertical, no more. So this is a sample free body diagram. Okay, the next one is freeboard allowance. How do you just calculate freeboard, or how do you take the height of freeboard? So you have two combinations, wave run-up and wave setup. Wave run-up is RU, which is just this formula. You can use this equation, this expression. Once you get the wave height, then theta is downstream inclination angle, then you can calculate. But adjusted wind speed must be calculated first, because wind speed over water surface and over the ground surface may not be the same. In the ground surface, there are so many obstacles like buildings, trees, and other structures. But over water surface, it is clear. So just we install instrument just for measurement on the ground surface. So this just around the site, around the project site. Then once you have data, then you have to adjust over water surface using this equation. So this is empirical equation. Otherwise, you have chart. You can use chart. Any wind speed at any height, you can calculate using chart. You go just over the ground surface. Otherwise, you can adjust using this formula, adjusted wind speed or wind stress factor 0.589 times U to the power of 1.23. So U is just wind speed over ground surface in miles per hour. You substitute, then adjusted wind speed you get. Then once you calculate adjusted wind speed, you will take wave period using this equation, which is metric system, and or using this equation using English system. So English system and metric system. So once you calculate wave period in either of the equation, you will take wavelengths. You calculate wavelengths, which is just 5.12 t square. Just this is English system. Then wavelengths 1.56 t square. So the difference between this just wave period. If you calculate wave period in metric system in this equation, you will use this equation. Otherwise, if you calculate wave period using this English system, you will calculate using English system just wavelengths. So wavelengths in meter, wave period in second, pitch length in kilometer, and wind speed in miles per hour. So this is just wave run-up. Once you calculate wave run-up, then you go to wave setup or SU, just according to Zuider-Z formula. You can use this equation. This is metric system, this is English system. You can use either. So when we say metric system, adjusted wind speed is in kilometer per hour, fetch length is in kilometer, average depth is in meter along the fetch line. So under this formula, adjusted wind speed is in miles per hour, fetch length is in miles, and average depth in feet. So these are conversions you can use. 1 mile 1.6093 kilometer, 1 feet 0.3048. So total freeboard just due to wave action RU plus SU, wave run up plus wave theta. Then you can add other parameters. Just if you have hydrograph, inflow and outflow hydrograph, and also flood emergency and gauging station or rating curve, etc. Just you can add some height, then you will provide total freeboard for the dam structure. So the average, just average depth of water along the fetch line. So this is an example, just how to calculate freeboard, just due to wave action. So compute the freeboard allowance for the section of gravity dam shown below. You have fetch lengths. So this is fetch lengths, 6 miles, wind speed 35 miles per hour. So you have side slope actually, just to make inclination 0.7 to 1, 0.7 horizontal, 1 vertical. Then you have depths, 3 depths. You will take just average depths. So the first step is you have wind speed. So you have to adjust this wind speed over water surface using the above formula. And fetch length is shown here. And D1, D2, D3, then average take. Then you can calculate wave run-up, then wave theta. Okay, the last one is just exceptional loads. So exceptional loads are seismic load and ice. So seismic load, horizontal and vertical inertial loads are generated with respect to the dam, and the retained water by seismic disturbance. So you have either horizontal or vertical inertial loads. So when we say inertia, I think inertia is the resistance to the direction of motion. So when the earthquake acceleration is just to the downward direction, inertia will be to the upward direction. Similarly, for horizontal, if the earthquake acceleration is to the downstream side, inertia will be to the upstream direction. So we will see this one in the next slide. So inertia means just seismic coefficient times weight, which is just PM horizontal inertia force, plus or minus alpha H times W. So when we say alpha, just horizontal seismic coefficient, and vertical seismic coefficient times multiplied by that cross section of the weight. It could be W1, W2, etc. This is total weight. So operating through the centroid of the dam. Otherwise, if it is not operating, the dam may be failed by earthquake. So ice load, actually, it is not a problem in Ethiopia, but take pressure of ice 145 kilonewton per meter square for ice more than 0.6 meter thickness. Otherwise, you can neglect. Okay, so the next one is effect of horizontal acceleration. We will see for reservoir full condition and for reservoir empty condition in the next slide. If you have any question, please forward using Telegram or email. Thank you. And thanks for watching this video. So this is all about today's lecture. Hopefully you liked the video. If you have any comment or question regarding this topic, please write down in the comment section below. I will reply on it. Please like, share and subscribe this video to get more precise lectures. Thanks.